Hello everyone, here we'll be discussing 4.5, which is a summary of curve sketching. And basically what this section tries to do is combine everything we learned up to 4.4 in an attempt to use that knowledge to, graph a function by means of calculus, so by hand basically. And that actually can be done using calculus provided you can solve certain things by hand. Now let me say here I give some guidelines of about 8 items here. But really these three are where we actually start to see usage of items from 4.5, 4.1 and 4.3 specifically. 4.2, the mean value theorem isn't really used for curve sketching too much. Maybe there's a way of kind of implementing that, but we're not really going to. 4.4 really comes into play when you consider asymptotes, because asymptotes are where you kind of discuss limits actually. So here let me just say this is 4.1, 4.3. This is where the actual calculus happens. And this is limits, possibly 4.4. Sometimes you don't even need to consider limits. Usually vertical and horizontal asymptotes of rational functions, like this example we're about to see, is something that's discussed in algebra that can be handled in a less technical way, but also kind of show the other way of doing it with limits as well. And then these three are, of course, algebra ideas: finding domain. A range I don't mention, but that's something you can also kind of consider. But usually what you'll do is you'll just kind of consider the domain of the function and break that up into sections maybe, and then kind of see what the graph does based on there. So the range will kind of come in due time. Intercepts are where obviously the graph passes through either the x-axis or the y-axis, and you just set the opposite letter equal to 0. Symmetry, we've kind of spoken about a little bit, I think, maybe. An even function means that if you take a negative value of that function, you just get back that function itself. An odd does the opposite, the negative pops out. And periodic basically means that if you add some number to the function, you get back the same function. So a really common example of periodic would be like 2 pi with sine and cosine. So notice sine of x plus 2 pi is just equal to sine of x, and same thing for cosine. In fact, even an odd also applied to cosine and sine respectively, but there are other functions out there. In fact, even powers and odd power functions are good examples of even and odd functions. But we'll see that as we go along. One thing I want to say as far as so these are guidelines. You can kind of treat it as a process maybe, run through this guidelines in order. And in that case, sketching will be the last thing, of course, but here's where I say we kind of put it all together, but possibly as you go along, meaning you may actually sketch as you run through the process. Don't just do it at the very, very end, but you can. It's up to you. But here I'm going to try to do it as we go along. So for this one, I believe we have enough space here, so we're going to want to graph this. Now the first thing I want to consider is the domain. Now in this case, I give some examples here of domain. The main three that come up really are radicals, when you have denominators, and then when you have something inside of ln, or natural log. In fact, any log for that matter, the inside cannot be 0 or negative, so it must be positive. Here x cannot be 0, the denominator can be 0, and here the radical can have a negative on the inside. And this is true for an even index radical. Even index. So if it's like the 4th root of x, or the 6th root of x, or the 102 root of x, something like that. But if it's an odd root, then the domain is negative infinity to infinity. In fact, the inside can be anything, let me just say. In fact, again, these are kind of the only three, I think, that have very specific ones. Well, there are some others that kind of come to mind, like tangent, for instance. But since tangent sine over cosine, this rule here applies. The denominator can be 0, and cosine, its denominator is 0 for certain values. Anyways, let's see here. So for domain, when can the denominator not be 0? Well, if you were to consider setting the denominator equal to 0, of course, if you add 1 to the other side in the square root, you get x is equal to plus or minus 1. And in fact, really, this is where we have vertical asymptotes. And that's something, again, that's kind of from algebra, that if you have a rational function when its denominator is 0, that's where you have these so-called vertical asymptotes. So we have at x equals -1 and at x equals +1. Now, in the context of limits, we can actually find the limit as x approaches -1 or +1 from each side. In this case, if we approach -1 from the right or left, we'll get, I think it'll be positive no matter what. Maybe we can try it. So notice when you plug in -1 from the right or left, it doesn't actually matter for the numerator. The numerator will still be the same value. Well, it'll still have the same sign anyways. What about here? Well, let's say if you plug -1 from the left, then you're approaching numbers that are smaller than -1. So like let's say -1.01 or something like that is a good example. When you square it, you get a positive number bigger than 1, so this is positive. But when you plug in a number that's bigger than -1, close to -1, like 0.9, that squared will be less than 1, and that'll result in a negative. So in actuality, we have this kind of a thing going on like this. So from the left, it approaches infinity, but from the right, it approaches -infinity. Just to get an idea. And similarly for the other asymptote, it does the opposite. But I'll allow you to kind of see that as you kind of try those limits. Okay, what about intercepts? Well, this is only equal to 0, so y would be 0 in that case for x-intercept. A fraction is only 0 when the top is 0. And notice the top is 0 when, well, x squared is 0, and that's when x is 0. So in fact, it has to pass through 0, 0, which is the origin. So in fact, it looks like it may look something like this. And this kind of about does it for the graph, and we're basically done. But now symmetry, it looks like there's, the way we drew it anyways, it looks like there's y-axis symmetry, which would imply that that's an even function. Since the only powers involved are even, then it is an even function. And in fact, you can see if you replace x with -x, you get back the same thing. If you were to replace x with -x, and a negative pulls out from the whole thing, and you get negative the original, then it's odd. But if neither of those two things happen, then there's no symmetry. Okay, good. What about asymptotes? We saw vertical, but for horizontal, we need to take limit as x goes to positive or negative infinity. But you'll notice as x goes to positive infinity, we have the same highest exponents on top and bottom. And in fact, you can kind of see from L'Hopital's rule as well. If you take derivative of the top, you get 4x, because we'll have infinity over infinity, so L'Hopital's rule applies. You'll have 4x over 2x. Take derivative again, because it's still infinity over infinity. You'll get 4 over 2, which is 2. And in fact, the algebra way of seeing this is if the powers are the same for a fraction of polynomials, you just look at the numbers in front for both of them, and you just get y equals 2 over 1. So in fact, there is indeed actually a horizontal asymptote, but that occurs at y equals 2. So not to scale here. Let me draw this dotted horizontal line like this. And that is y equals 2. And it's a horizontal asymptote, so this curve here does something like that. Now, so far I've used only the algebra things, I kind of spoke about L'Hopital's rule a little bit for the limit part for asymptotes, but I haven't used any of the calculus stuff. It kind of came together. I mean, I had to know that it curved like this, but how else could it curve if it has these asymptotes? So that's something you may want to consider. But at least it gives you an idea of how these things will behave. And in fact, we can kind of do it real quickly. If you were to take the derivative of this, you'd have to use quotient rule. So that would be all over the bottom squared. So this is y prime. And now for numerator of quotient rule, it's derivative of the top times regular of the bottom minus regular of the top times derivative of the bottom. And notice what you end up getting after distributing is 4x cubed minus 4x minus, this is also 4x cubed. So notice in this case what happens is the 4x cubes cancel, so you get negative 4x over this denominator squared. And what this tells me is that, well, let's see, does it mean that it's always negative? Not really, because x could possibly be negative as well, so you get a double negative. The denominator is always positive because it's all squared, that's fine. But it's either positive or negative depending on x. And in fact, you can kind of tell. When x is positive, you'll have negative times positive, so it'll be negative. So when x is bigger than 0, y prime is less than 0. So I'm not really writing it down, I'm just kind of talking it out. And really what that implies here is decreasing, because when the derivative is less than 0, then it's decreasing. And you can tell when x is bigger than 0, here the function is going down, here the function is going down. So it is indeed decreasing there, and increasing when x is negative, because when x is negative, you get a double negative on top. And again, bottom doesn't matter because it's all squared. And indeed, you can see when x is less than 0, when x is negative, the function is going up, the function is going up. Now, as far as local max and min, there appears to only be one at 0. And that makes sense because that's when our derivative here is equal to 0 is when the numerator is 0. Or when the derivative is undefined, which would be a positive and negative one, but we have vertical asymptotes there. So that's why I say where it's undefined or where it's equal to 0 give candidates. So it's not always going to be the case that setting the derivative equal to 0 or undefined will automatically give you local max and min x values, but it'll give you possible ones. So I call those candidates. Now as far as concavity goes, we need to find the second derivative, which seems a little wild. But I don't think it's, I mean, maybe we can do it. Just for time's sake, I'm not going to do it, but I'll allow you to do it on your own, of course. So find y double prime, I found y prime here. So finding y double prime won't be too bad, but I'll tell you right now, based on the asymptotes, it has to be like this anyways, but it's nice to check with the second derivative that from negative infinity to negative 1, it'll be concave up, so it opens up. From negative 1 to 1, it's concave down. And from 1 to infinity, it's concave up. And I think that's going to be when the denominator is 0, which totally makes sense because you'll have an odd power there. Well, it's not obvious, but you'd have to take the derivative again, and then you'll get cancellation so that the power is actually odd and not even. Anyways, we're going to do some more examples that are a little more involved than this one was, but this was a nice walkthrough of the guidelines. So let's take a look at a few of those, and that'll actually be the end for 4.5. Alright, so the previous example we just did was, of course, a rational function, so it's a fraction of polynomials. And as mentioned, that's kind of not too hard to graph, even if you don't know calculus. Of course, you need to have the understanding of asymptotes. So once you have that, it's not too difficult. The concavity kind of comes on its own, and max and min's kind of as well. But I'll leave it to you to kind of figure that out and maybe try some different examples. I'm not going to be doing really any of those rational functions. We'll do one after these two, actually, that'll involve radicals. It may have a kind of fraction behavior to it, but we'll have to see when we get to that. But for these two, well, of course, I'm going to start with the first one. And let's kind of course, just consider the guidelines we saw in the same order that we saw them for the previous example. So here first we're going to consider domain. And for domain of ln of something, we want the inside to be positive and non-zero. So I'm going to set this inside equal to being greater than 0. And notice in doing that, we get x cubed is bigger than negative 1. So after cube rooting, we get x is also bigger than negative 1. So that's our domain. Meaning we actually get at x equals negative 1, this kind of vertical asymptote here. And if you kind of consider how the graph of ln of x looks, it has an asymptote kind of like this, but on the y-axis. And what that also kind of tells us is that as x gets closer to negative 1 from the right, because again, this tells us our domain is only from negative 1 to infinity, so we can only approach x equals negative 1 from the right anyways, then the inside will approach, well, it'll approach 0 actually, because when you plug in negative 1 into the inside, you get 0. But 0 is being approached from the right, and ln of, well, x, where x approaches 0 from the right, approaches actually negative infinity. So what it tells me is that the graph looks like this on that side of the asymptote, and of course on this side there's nothing going on because it's outside of the domain. All right, so now we considered that, and then we got a vertical asymptote out of it, which is great. Now for the x-intercepts, if you actually let y equals 0 to find the x-intercept, you can take, notice you can take e to both sides. E to the 0 is 1, e to the ln cancels, you just get the inside, and this implies that x is equal to 0. Of course, if you subtract 1, you get x cubed equals 0, cube rooting gives you x equals 0. So we actually have this point 0, 0 as a point on the graph that acts as an x and y intercept. In fact, it's the only one really, and that's kind of what this tells us. And also notice as x goes to positive infinity, the inside goes to infinity. And ln of x goes to infinity as x goes to infinity. So that means this goes to infinity as the inside goes to infinity. So we'll have something like that, kind of. And in fact, it could, I made it look like it's concave up, it could be concave down. So we may have to change this. So again, I'm kind of sketching as we go along. But now finally we get to the scenario where we have to apply calculus. So what we're going to do now is find y prime and then y double prime to discuss concavity, but then before that, of course, extremis. So let's see. Y prime, notice, is derivative of the inside over original inside. That's how you take derivative of ln of something after all. And like we discussed previously, to find good candidates for max and mins, we need to see where the derivative is 0, meaning the top is 0, or undefined, meaning the bottom is 0. Now when the top is 0, that just gives you x equals 0. When the bottom is 0, that gives you x is equal to negative 1, which is not good because negative 1 is not in the domain of our function anyways, so this actually doesn't give us anything. So now we're going to consider this 0 and plug numbers around 0. But notice the smallest value we can plug in to this expression we have is negative 1. So this number line really stops at negative 1. But it can go up to infinity. So here we'll pick, let's say, negative 1/2. When you plug negative 1/2 into, we want to plug it into y prime to check the sign for y prime. When you plug a negative 1/2 into y prime, well, the denominator will be 1 minus 1/8, which is positive. And the top's always going to be positive because of the square. So that's fine. And now we'll plug in, let's say, positive 1 here, and you'll also get a positive value, actually. Notice you get 3 over 2, which is positive. So this tells us our derivative is always positive, meaning the function is always increasing, so there are no dips in between, actually. So, great. It also tells us that there are no max and mins, so let me kind of write that here. So for max and mins, there are none. Max and mins, there are none, unfortunately. And for increasing, it's increasing on the entire domain of the function, which is negative 1 to infinity. And now we need to find the second derivative, and of course that will involve the quotient rule. So let's consider doing that now. So we have y prime, that's fine. But now we need to find y double prime. So let's see if we can do it all in one shot. So y double prime will be all over the bottom squared. So that's 1 plus x to the third squared. Derivative of the numerator, well, derivative of this by quotient rule, the numerator will be what? Quotient rule numerator would be derivative of the top times regular of the bottom minus regular of the top times derivative of the bottom, just like this. So actually after combining, we end up getting 6x plus 6x to the fourth minus 9x to the fourth. Notice these actually combine to negative 3x to the fourth. And if you actually factor this out, you can factor 3x out of this, and you get 2 minus x to the third. That checks out. Great. So now, just like we did with the first derivative, we want to see when this expression here is either 0 or undefined. But it's 0 when the top is 0 and undefined when the bottom is 0. And in fact, the bottom is never 0. Well, actually, the bottom can be 0, excuse me. The bottom can be 0 again when x is negative 1, but that's something that will never actually happen because negative 1 is not in the domain of y. So really, this is equal to 0 when the top is 0. Now the top is 0 when either 3x is 0, meaning x is 0, or when 2 minus x to the third is equal to 0. And notice adding x cubed to the other side gives you this, and then cube rooting finally gives you the cube root of 2 is equal to x. So that'll be, let's say, over here. In fact, I guess that's fine. Let me actually move this, just for space. Perfect. Now again, before 0, we can plug in negative 1/2. In between these two, we can plug in 1, and after these two, we can plug in 2. Just to be kind of simple about it. Now we're going to test for the sign of y prime, y double prime actually. So let's see if we can figure out what these are. And it's best to leave it factored, notice, so we can just check for sign. When you plug in negative 1/2, notice the bottom is a square, so it's always going to be positive. The top will be 3 times negative 1/2 is negative. 2 minus negative 1/2 to the third is 2 plus 1/8, which is positive. So this will be negative here. So it's concave down there. Here, when you plug in 1, in between 0 and cube root of 2, when you plug in 1, you'll get 3 on top. 2 minus 1 is 1, so it's positive on top. Bottom, again, is always positive. So this is positive. When you plug in 2, however, that's going to be 6. 2 minus 2 cubed is 2 minus 8, which is negative 6. So it's positive times negative will be negative. Awesome. So from this, we actually have an understanding of concavity. And we know inflection points are a thing because we have change in sign of the second derivative. Great. So let me see if I can write that here. I'm going to have to erase this. So let me, let me do this. I'm going to erase y double prime. I'll move it over down here though, and then I'll summarize the rest of concavity based on this. All right, so based on the way we solved an inequality with a number line we had previously, we had that it was positive, the second derivative that is, was positive between 0 and radical 2 or cube root of 2, negative between negative 1 and 0, and between a cube root of 2 and infinity. So it's concave up in this interval and concave down in this interval or this interval. So the union means or, of course. Now the inflection points are the x values that had a sign change between the second derivative, which are 0 and cube root of 2, because on either side of those, plugging values in between, not in between, but plugging values that are surrounding these numbers will give you a different sign change, different sign that is. So there's a sign change around these numbers. Now if you plug these values into y, because of course these inflection points are points on the graph, meaning they're on the curve of the original expression here, plugging 0 will give you ln 1, which is 0. So 0, 0. When you plug in cube root of 2, cube root of 2 cubed is just 2, and 2 plus 1 is 3, so this is ln of 3. So it's cube root of 2 comma ln of 3. And now we're going to attempt to graph this. So the only real point that actually comes up is x equals cube root of 2, and then the y value, of course, would correspond to ln of 3. Awesome. Well, that should be next, sorry. There we go. So now let's see if we can figure out, again, the way the graph looks. So we know it's concave down between negative 1 to 0, so it's going to have to look like this, bending down. It's concave down here. I tried to make it look like that. Let me try to make that look a little more, putting more emphasis on that bend. Okay? And then this is a point on the graph as well, but from here to here it's actually concave up between 0 and cube root of 2. And then after that point, then it's concave down, and it goes off to infinity. So this is more or less how the graph looks. So it has these squiggles in between, but there are no actual dips or bumps in between because there are no max and mins. That was a pretty nice example. This one hopefully will be a little quicker, but let's take a look. So in fact, what I'm going to do first, I think, is again, we're going to look at domain. So let's see if we can figure out what the domain is looking like. There appears to be no symmetry when you replace all x's with negative x's. Here in the denominator stays the same, but the numerator, e to the negative x, is different than e to the x. So there's actually no symmetry, unfortunately. But at least we saw that with the previous example before doing this one, so that's okay. But again, domain x cannot be 0 because then you have a 0 denominator. E to the x is, well, that's always defined. So really this whole thing is undefined when x is equal to 0. So it appears that on the y-axis there's maybe this vertical asymptote. So let me just write x equals 0 here just to kind of emphasize that this is maybe a problem. And in fact, notice that if you plug in values that are either to the left or to the right of 0, x cubed will always be positive. So in fact, this tells me that this will approach positive infinity as x goes to 0 from the left or from the right. Okay. And that I think makes sense again because as x goes to 0, this is going to be positive. In fact, you can kind of tell. E to the x is always positive no matter what you plug in for x. X squared also is always positive. So that tells me that the range actually is above the x-axis, which is kind of interesting. So we're going to have this kind of a thing going on. And again, let me try to draw the graph in red. So we appear to have this vertical asymptote like this, approaching the same side on the same direction on each side of the asymptote. But now for the horizontal asymptote, what happens as x goes to infinity? Well, as x goes to infinity of this, you You may need to use L'Hopital's rule because you get infinity over infinity, but it's not difficult to see that if you apply L'Hopital's rule, your limit will still be the same, but notice derivative of the top is still going to be e to the x. The denominator will eventually go to a constant. So after a few tries of L'Hopital's rule, in fact one more time, I think we'll do it. Yeah, there it is. You get e to the x over 2. So L'Hopital's rule is no longer applicable. And you get infinity over 2, which is infinity. So as x goes to infinity, the function goes to infinity. So you'll have something much like we had for the previous example up here. The concavity is still to be seen though. But what about as x goes to negative infinity? Well, as x goes to negative infinity, the bottom will still approach positive infinity. The numerator will approach 0 though. So 0 over infinity is not an indeterminate form. That actually just straight up approaches 0. Because it's 0 over infinity. Let me think about that a little more. Yeah, that'll still approach 0. So in fact, we have a horizontal asymptote this way. Something like that. And again, that's because as x goes to negative infinity, this expression goes to 0. And that can't be proven using L'Hopital's rule. You just have to kind of see what happens with each of them. The bottom approaches infinity, top approaches 0, 0 over infinity will approach 0. Okay. So I hope that's okay. But now what? Well, now I think we have no choice but to consider derivatives so we can talk about concavity and maximums. So, and I actually haven't done any intercepts. But again, these are always positive, so there are no intercepts. In fact, there are no intercepts on the y-axis either. Notice if you set x equal to 0, it's undefined. If you set y equal to 0, you get problems. But I'll just kind of show you. If y is 0, you get this. If you multiply x squared to the other side, you get this. And e to the x is never 0, actually. In fact, if you try to get rid of the e by taking ln of both sides, you'll get ln of 0, which is a negative infinity. So that tells you that it gets closer to 0 as x goes to negative infinity, which in fact we kind of showed earlier. So it's nice to see that, but it's unfortunate in some sense we don't have any x-intercepts, or even y-intercepts for that matter. All right, so now, to consider the first derivative and even second derivative, I am going to try my best to bypass quotient rule. I'm going to write this as a product. I'm going to write this as x to the negative 2, e to the x. We still have to use product rule here, but not quotient rule though. So then y prime would be negative 2x to the negative 3, e to the x, plus e to the negative 2x, e to the x. Notice taking derivative of one at a time. So derivative of the first, regular of the second, plus regular of the first times derivative of the second. We end up getting this. And I guess we can factor out what they have in common. So notice the smallest power they have in common is x to the negative 3, and they both have e to the x. So we pull this out, what we'll actually have left is we'll have a negative 2 here, and this will have to be positive x to the, think of it like this, x to the 1, because if you distribute this back in, the powers will add, so x to the negative 3 times x to the 1 is x to the negative 2 now. Okay. In fact, I'm going to write this, if you don't mind, as x minus 2. Now, I know this is a little bizarre, but honestly, this is the best way of factoring this kind of thing, because otherwise you have to write it as fractions by getting rid of the negative powers, and then combine those fractions into 1 by finding common denominators. You end up getting this anyways, e to the x times x minus 2 all over x cubed. So honestly, the best thing to do is look for the smallest power they have in common, even if it's negative, like x to the negative 3 here, and then pull that out by kind of considering, I guess, reverse distribution, or just adding the power. So notice here, when I said we lose a negative 3, so there was no x here, really just we're adding 3 to each power. So if you add 3 to each power of x, you get x to the 0, so no x for that term, so it's just negative 2. And adding 3 to this, we'll get x to the negative 1, or x to the positive 1 actually, which is just x. Great. But now, when is x 0? Well, this is never 0, because it's a negative power. E to the x, as we saw earlier, is never 0, but this is 0. This is 0 when x is equal to 2. So in fact, that's the only value we have to test around 2. Into the first derivative, and we're going to check for the sign. So I'm going to check, well, let's see, we can pick any value you want. You can plug in 0 though, because 0 is not in the domain. In fact, notice it's not even in the domain of the first derivative. But we'll plug in 1 and then 3. I think that'll be okay. And we're just checking for sign, notice. So when you plug in 1, let's see, this is positive. 1 to the negative 3 is positive, e to the 1 is positive. Here, this is going to be 1 minus 2, that's negative. So positive times negative is negative. Plugging in 3 though, 3 to the negative 3 is positive, e to the 3 is positive. 3 minus 2 is positive, so positive times positive is positive. Great. So we have increasing and decreasing. Hang on a second though. There's a little bit of an issue. Aha. So notice I'm setting these equal to 0, but remember that the derivative, well, notice that you have candidates for extrema when the derivative is either 0 or undefined. So technically this x to the negative 3 is never 0 because it's a negative power. But if you wrote this as a fraction, like I kind of mentioned, so we probably should have done that, actually. You want to set top and bottom equal to 0, kind of like we did with the previous problem. When you set the top equal to 0, you just get 2. But when you set the bottom equal to 0, you get 0, actually. So we actually should have still tested around 0, so I'm going to modify this a little bit. So we should have picked a number that's less than 0, like negative 1. And the reason why I was able to catch myself with this small mistake, kind of, was that I looked here and I saw, okay, well, it's increasing, decreasing, but then increasing again. But from only considering the number 2 and these numbers around, we get decreasing and increasing, which I see decreasing and increasing, but this increasing we didn't see. So now that tells me this should possibly be positive, and it is going to be, but notice, I'll just show you, when you plug in negative 1, we get e to the negative 1 is positive, negative 1 minus 2 is negative 3, that's negative, so the top's negative, but negative 1 to the 3 and the bottom's negative, and negative over negative is positive. So this is actually positive. So it's for sure increasing here, decreasing, then increasing. So there are no bumps in between, just this little bump here possibly, because notice the sign change here at 2. At 0, there is a sign change, but notice 0 can't be plugged in, so that's just an asymptote actually. If you think of infinity as a max, maybe you can see that, like spike kind of thing, but we don't really see it like that. We see it more as an asymptote. All right, so I'm going to, let me do this. I'm going to write the facts that we have, kind of like these facts over here, and then I'll erase some of this, and then we'll move on to second derivative. All right, so based on that number line we just had before I erased it, it was positive from negative infinity to 0, and also from 2 to infinity, so that's our intervals of increase, and then negative from 0 to 2, so that's our interval of decrease. Now as far as max and min goes, well, we can actually tell that, again, there was a sign change between 0, but that corresponded to a vertical asymptote. Between 2, the sign change was, well, it was a negative and positive. And we can tell because it's going down, then going up. So it's okay that I erased it, but you can kind of see. It's decreasing from 0 to 2, and then increasing beyond 2, beyond x equals 2. So at 2, there's a minimum. So there's a minimum for sure at, so let me just write min only. So there's no maxes, actually, it turns out. But there is a minimum. And where is the minimum? Where does the minimum occur? Well, it occurs at x equals 2, so allow me to write it as a point. Actually, I won't write it as a point. But to figure out what the minimum is, we of course need to plug it in. So when you plug in 2 into the original, you get e squared over 4. So it's e squared over 4, and it occurs at x equals 2. And remember, that was our language we developed for max and mins. It's the height at that x value. So e squared over 4, let's just say that's over here. Since e is about 2.7, e squared is going to be a little less than 9. And 9 over 4 is about 2.25, so it's somewhere in that ballpark, probably a little smaller. So let me just draw that point here in red. So it's going to look something like this maybe. We still don't know as far as concavity is concerned, so I'm going to kind of wait on that. But from what I can tell, it looks like concave up everywhere. Well, we don't really know. For all we know, there are some squiggles in between somewhere. And it's not going to take too much effort for us to find that because we need to find the second derivative. Now notice we have 3 parts of the product here. I wrote it like this. because writing like a fraction will require us to use quotient rule, and I'm going to try to bypass quotient rule if possible. In this case, we definitely can do that. The only issue that I'm having though is that these are, again, 3 parts of the product. So there are a few ways we can do this. In fact, I know it's a little roundabout, but let me just kind of show you. If we distribute this, we get x to the negative 2e to the x minus 2x to the negative 3e to the x. So we'll have to use product rule twice here, but I think it's okay. There is a version of the product rule that I may or may not have shown where you have 3 parts of the product. So instead of uv, it's uvw. And the product rule there is actually pretty cool, but it's I don't want to use that if we don't have to. So here we can just do this. So product rule for each of these. So for the first one, we're going to have derivative of the first, regular of the second, so this is for y double prime, plus regular of the first times derivative of the second. So that's the derivative of the first term using product rule. Then derivative of this one, so we're going to take derivative of the first, so it's going to be positive 6x to the negative 4, good, times regular of the second plus regular of the first, which is negative 2x to the negative third, times regular of the second, which is e to the x. Great. Now something's combined. Notice that these here combine to negative 4x to the negative third. And I guess we can write this in kind of from largest power to smallest power. So it's x to the negative 2e to the x. These two again combine to negative 4x to the negative 3. And then we have 6x to the negative 4e to the x. And much like we saw with the previous first derivative, we're going to pull out what they have in common. And the smallest power of x they have in common is x to the negative 4th. And they're not all divisible by the same number. This having no number in front kind of ruins that. But that's okay. So we're going to pull out x to the negative 4 and e to the x. And in doing so, what we'll have left on the inside are just going to be powers of x basically. And basically taking out x to the negative 4, all we need to do to see what those powers are is just add 4 to each of these powers. And again, ignore e to the x because we're pulling that out. So adding 4 to this gives us adding 4 to this power gives us x to the 2, minus 4x, because 4 added to negative 3 is just x to the 1, which is just x. And then here we only get the plus 6. Perfect. And is this factorable? I don't believe it is. Maybe, just maybe we can use the quadratic formula here. I think it'd be actually nice to do that. There's another way of doing this by completing the square, but I hope this has no zeros. But the best way to check honestly is by quadratic formula. In fact, just to check that there are no zeros, I'm going to try to find the discriminant part of the quadratic formula. So I'm going to focus on, so the quadratic formula has all this other junk, but I'm going to focus on the inside of the radical. And if the inside of the radical is negative, that means this has no real solutions. So it's either always positive or always negative because it's never 0. And it represents a parabola. So either it's a parabola completely above the x-axis or completely below the x-axis. And notice since it has a positive coefficient, it's opening up. And if it was below the x-axis opening up, it would have to cross the x-axis. So this is always going to be positive if there is no solution. So now remember the discriminant is b squared, it's negative 4 squared, minus 4 times a times c. So notice here we get negative 4 squared is 16, minus 24 is negative 8. So this actually has no solution because the discriminant of the quadratic formula is negative. And in fact, there's another way you can do this by completing the square. If you wrote this as x squared minus 4x plus 4 plus 2, x squared minus 4x plus 4 is actually the same as x minus 2 all squared. Like this. Which tells you that this is never 0 because no matter what you plug into x, this will always be positive and a positive number because it's squared. And positive number plus 2 is always positive. So that's another way of seeing that actually, which I think is kind of better. So good. So that means this is never 0, e to the x is never 0, x to the negative 4 is never 0, but its denominator is 0 when x when this is equal to 0. So when x to the negative 4 is equal to 0, the bottom is equal to 0. So we actually do still need to kind of check those around with the sign of the second derivative. Good. So that's y double prime. And the only value we got by setting the numerator and denominators equal to 0 was 0 itself. Testing numbers around these, we have complete freedom here. So I'm going to choose -1 and 1. We're going to test into y double prime, check for the sign. Notice this guy here is always positive, as we just saw. This guy here, as we saw earlier, is always positive. X to the -4 actually is always positive too, because it's an even power. So there's not really much to check. In fact, if you try plugging these in, I'll just tell you right now, it's going to be positive everywhere. Meaning that we actually are not concave down, but we're only concave up on the whole real number line. I guess with the exception of 0, but I'm just going to write it like this. So it's concave up here and here. And the inflection points, there aren't any because it's always concave up. Which I wrote a sad face, but in reality it's kind of good news because it's less to do. So here we can connect these like this and connect this finally like this. Great. So we can now see the concavity indeed is true here like this. It's always concave up. Unlike the previous one had some kind of squiggles. So now I said I wanted to do one example involving graphing a function containing a radical. I think these were really excellent examples. In fact, this is probably the core of the video, you might want to say. But now I'm going to erase these and move on to that one last example, and that'll be the end finally for 4.5. All right, so here we're being asked to graph this equation y equals x minus 3 in parentheses multiplied by radical x. Now, to find the derivative of this, we need product rule, but there's a way to bypass that. In fact, if you write this as x to the 1/2 and distribute this in, we actually get x to the 3/2 minus 3x to the 1/2. So in fact, really all we need to do is just apply power rule to find the first derivative. So you may want to jump to that, but of course, questions of domain and asymptotes kind of come into play. But I'm actually just going to kind of move around in a maybe not obvious way. So I'm actually going to find the first derivative and then second derivative, because that was the majority of work we saw. The rest was just, having the understanding of domains and asymptotes based on other things. So I'm just going to focus on the calculus part first. So this is still y, not y prime yet. Now y prime will be 3/2 x to the 1/2 minus 3/2 x to the -1/2. And much like we saw in the previous example, we can pull out, in this case, 3/2 x to the smallest power is -1/2. And to do that, you just add 1/2 to each of the powers. So adding 1/2 to this gives you x to the 1, which is just x, minus adding 1/2 to this is x to the 0, which is just 1. And this is good because we can set each of these equal to 0. This will be where the denominator is 0 because it's a negative power. So what we end up getting actually is x is either 0 on the bottom 0 or positive 1 when x minus 1 is 0. And plugging the numbers around these, well, now we may possibly have to consider domain. And in fact, just looking at this, x can't be negative because we had the square root of x. So in fact, nothing exists over here. So this number line really stops here, actually. But we still can check test numbers around 1, so that's okay. So we'll test 1/2 and 2. So again, all we're checking for is sine of the first derivative, and it's factored for us already, which makes our job a lot easier. Plugging in 1/2 will give you 1/2 minus 1 here, which is negative. 1/2 to the -1/2 is a positive value. It's just going to be in the denominator. So the negative power doesn't affect the sign. So this will actually be negative. Plugging in 2, 2 minus 1 is positive, 2 to the 1/2 is positive. So this is going to be positive. What the actual number is, again, I'm not figuring that out. I'm only figuring out the sign, because that's all we need to find out if we're increasing or decreasing. So now we found out that we're increasing on the interval 1 to infinity, looks like. So this is infinity. So from 1 to infinity, we're increasing, and we are decreasing from 0 to 1. Great. And notice there's a sign change here, so we actually have a max or a min. And since we're going down and then going up, which is honestly the best way of seeing it, which I wish I could have shown in the previous example, but that's okay. I kind of explained it in words, but still, going down and then going up implies there's a minimum here. So there's actually a local minimum. It may actually be an absolute minimum, but who knows? We'll find out when we actually graph and put it together, maybe. In fact, I think we kind of tell it has to be absolute because it doesn't go down below this. There's no other minimum. Okay, and it's at 1. So what is the value at 1? When you plug 1 into the original thing, you get 1 minus 3 is negative 2. Negative 2 times the square root of 1 is just negative 2 times 1. So it's negative 2 at x equals 1. Awesome. Perfect. Now maybe we can try to piece together what's going on with the graph. Because I'll admit, doing things like the way I just did it is probably not the best because as we saw previously, if you piece it together as you go along, it starts to make more sense and you can kind of guess and check certain things. So again, we saw that for domain, x cannot be negative because we had the radical. So we're only dealing with the positive x-axis part of things. Okay, now as far as intercepts go, when you plug in 0 for x, square root of x is 0, so the whole thing turns to 0. So 0, 0 is a point. For the, is that the only? I guess not. Because when y is equal to 0, that's either 0 when x is 0 or when x minus 3 is 0. And notice x minus 3 is 0 when x is equal to positive 3. So let me go over here to 3 on the positive x-axis. And 3 comma 0 is going to be a point. Okay. Now what have we found out? Well, we found out that at x equals 1, there is a minimum at negative 2. In fact, you kind of see it has no choice but to be the absolute minimum because it goes down from here to here and then goes up and doesn't go back down actually. Now again, we still don't know much about anything else. Of course, we can try to find limits and horizontal and vertical asymptotes, but there don't appear to be any because this is kind of always defined. There's no zero denominator or anything like that happening. Again, the radical just means that there's kind of like this sudden stop at 0. But if you, again, recall how the graph of square root of x looks. The graph of square root of x looks like this. There's an abrupt stop at this point with no asymptotes. So this doesn't appear to have any asymptotes. Notice as x goes to infinity though, this goes to infinity and that goes to infinity, and infinity times infinity will go to infinity. So we have roughly this idea where it kind of looks something like this, but there's a little bit of a curve in between. Okay, so now I'm going to erase a bunch of this and then move on to the second derivative to continue. All right, so I erased a lot here and I just shifted y prime up here, so now we can find y double prime and then move on to discuss the concavity and inflection points, if any. So to find the second derivative, again, I'm going to treat this as a product, so use product rule. So derivative of the first is going to be negative 3 over 4 x to the negative 3 halves. Hope that's not too hard to see. Actually, we don't need to use product rule, do we? We can just distribute this in. In fact, that's how we handled the first derivative. So let's just do that actually. Maybe it'll make our lives easier. So we get 3 halves x to the negative 1 half plus 1 is positive 1 half minus 3x to the negative 1 half. So if you were to use product rule, you notice you'll get the same thing we're going to get here after finding the second derivative now. So doing it this way, combining first, if possible, will take care of any like terms that would have combined after using product rule, which is nice. So now derivative of this, notice is 3/4 x to the negative 1 half, which is kind of what we got first, but we didn't go beyond that. And then derivative of this is going to be positive 3 halves x to the negative 3 halves. Yeah, so now thinking about it, we got negative 3 halves, not negative 1 half. But it doesn't matter. Anyways, we end up getting this for the second derivative. And now again, we're going to pull out what they have in common. And actually, I'm going to pull out the smaller values. Let me see here. I'm going to try to take a tip from what we've been doing. So if we pull out 3/4, the smaller coefficient, I think this works. Yeah, let's try this. So pull out 3/4 and then the smaller power is negative 3 halves. On the inside, what do we get? Well, there's no 3/4 and then you have to add 3 halves to everything now, every power of x. So 3 halves minus 1 half is just 1, so that's x, plus, so here what we did is we pulled out the 3 on top, but then we divided by 4. So what does dividing by 4 do? Well, remember, if you divide everything by 4, you're multiplying by 4. So think of it like this. to make this a 1, you multiply by the reciprocal of 3/4. So that gets rid of the 3, but then multiplying by 4 makes it 1. So multiplying this by 4 will make it 2. And now adding 3/2 to this power is no power. And I know this sounds weird, but again, if you distribute, that's another way of seeing it, that it actually works out. When you distribute this in, you get the first term. Distributing this into the second term, 2 times 3/4, notice, cross cancels to 3/2. So that's nice that you can see that, hopefully. And now, the values we get, again, when the denominator is 0 is at 0, and when this is equal to 0 is at -2, which is actually before 0. And that is actually very, 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 very bad news, kind of, because -2 is not in the domain. Remember, we're only considering the right half because negative numbers can be plugged into our original function, as it turns out. So -2, x equals -2 doesn't do anything for us. So in fact, the numbers that we can really plug in between these are not here, but here we can. So we'll plug in a number, but notice 0 to infinity is literally our domain. So whatever this sign is, it's always going to be either concave up or concave down. And based on what I got here, I even drew like a little U here, I'm assuming this is going to be always concave up, but for all we know, it could always be concave down, where you'd have like this kind of sharp point here, so it would look something like this. That is totally possible, kind of looks like a check mark. But I don't think that's the case because this 1 we got here for our max and min, or for our minimum, I guess I should say, came from setting the top equal to 0, not the bottom equal to 0. So the derivative was indeed 0 at that point. So we have a horizontal tangent line, not a vertical one. So, but it's always something to consider. So I hope that helps. But now let's see. Let's actually plug in 1 to our second derivative and see the sign finally. And you can tell right away, plugging in 1, that's positive. 1 plus 2 is 3, that's positive. So indeed, this is always concave up on our domain, which is 0 to infinity. Okay, this is never concave down, and there are no inflection points because it's always concave up. There's no sign change in the second derivative. In other words, there's no change in concavity at all. So this image will actually straight up look just like this. Just like this kind of U parabolic kind of shape. Which isn't super surprising because this is kind of like a polynomial. It's not quite a polynomial, but again, if you distribute, you get x to the 3/2 minus 3x to the 1/2. And it's kind of polynomial looking like, so we're expected to get something that will remind you of a graph of a polynomial, but radicals may change things, and they could actually have spikes like I showed with a checkmark pattern. That's possible, totally possible. Awesome. So we only really saw 4 examples, but they were pretty good examples, especially the middle 2 I think were really, really nice examples for everything we saw essentially that you can use in chapter 4 to graph a function by hand. Awesome. So hope you enjoyed this, really did. Hope you enjoyed this. I thought this was pretty fun. I'll see you in the next video for 4.7. 4.6 is actually not covered because it is a kind of computer or calculator assisted graphing where you can employ these kinds of ideas and read it on your own if you'd like. But we're going to jump into 4.7, which is optimization, and that gets kind of into what we saw from related rates. It's going to be a lot of word problems. So that video I kind of expect to be kind of long, but it's going to be really challenging. I don't want to say fun. I mean, I always have fun with these things. You may not have the most fun time with it, but it's definitely challenging. It's going to make you think. So if you consider that fun like I do, then you're going to have fun. Let's just pretend we're all going to have fun. So I'll see you in the video for that. Thanks for watching. Hope you enjoyed, and I'll see you then.